Question 4. Let m less than n be positive integers. Start with n piles, each of m objects. Repeatedly carry out the following operation. Choose 2 piles and remove n objects in total from the 2 piles. For which pairs mn is it possible to empty all the piles?
I'm going to think about these objects as counters. It just seems a slightly nicer word than objects. And we'll start by noting some points. And some of these will be really quite obvious. But I'm just going to list some of the initial things that we find when we start playing with this problem. So first of all, we can see that n cannot be bigger than 2m, because that's the maximum number of counters that we've got in 2 piles. But in fact, if n is equal to 2m, then we can empty the entire lot of piles, because we can take 2 whole piles at a time, and because n is equal to 2m, we will have an even number of piles. So we can carry on doing that until they're all gone. Okay? Next observation. If n doesn't equal 2m, then it cannot be bigger than 1.5m. And that is because if we were to take something bigger than 1.5m from these 2 piles, in one of the piles we would have left a little bit that was smaller than half m, and we wouldn't be able to remove that by combining it with any of the other piles. Okay. But if n is equal to 1.5m, then this does work, because we can take 1/3 of the piles and cut them in half, and we can take each half and combine it with a full pile, and we can remove them in that way. We can keep on going until we have removed all of them. So we've got 2 families here that will work. m and 2m will work for any value of m, and m and 1.5m will work for any value of m. There's one more situation that quickly becomes apparent that will work, and that is when n is m plus 1. And that's because we can take one of these piles and think about them as individual counters, and then we can take each individual counter in that pile and combine it with a full pile. And because there are m counters in here, we can combine it with the m piles that we've got. So this is the 1 in the m plus 1 number of piles. So that will work. One other thing that quickly becomes apparent as you're working through this is that once you have got a solution, once you've got a pair of numbers that work, you can multiply those pair of numbers and get another pair of numbers that work. So if m and n work, then so will km and kn. And to see this, we can think about the kn piles, and we can split them up into sets of n piles. So we've got k different sets of n piles. And in each pile we've got km counters, and we can kind of tape those counters together in little bundles of k, so that we've got m bundles in each of those piles. And then we've got a setup very similar to this, and we can follow the same algorithm that we had for our mn situation, and we can clear up all of the counters in one set of n piles, and then we can move on and do the same algorithm in the next set of n piles. So once this works, we know that all the multiples of this will work. Okay, so I'm just playing around with this question at the moment. It's really useful to start listing the things that you notice, because some of these might be useful in your solution and some might not. But once you've got a list of things that you have spotted, you'll know where you want to investigate further. So after a bit more playing around with this problem, I started to feel like m and m plus 1 and multiples of this, km and km plus 1, might be the only possible pairs that worked. And it's worth noting that the 2 families that we looked at before both fall into this category. So m2m is just a multiple of 1, 2. And the other one that we spoke about was m 1.5m. Well, clearly that only works when m is even. And so that is just a multiple of 2, 3. Okay, so I have my conjecture now. My conjecture is that all pairs of numbers that satisfy the question are going to be of this type. And let's have a think about how we can prove that. Okay, so I'm going to start with values of n and m that work, and I'm going to let n be equal to m plus d. And d is positive because n has to be bigger than m. Then I'm going to consider a subset of piles. And I'm going to consider this subset so that all of the moves just use these piles. I don't need to use piles outside to remove counters inside this subset. It's a kind of self-contained set of piles. Moreover, I'm going to make sure that this is a minimal subset so that there isn't a smaller set inside that I could have chosen. And that means that all of these piles here are connected in some way. So maybe in my algorithm, I remove m plus d from these two, and at some point I might remove m plus d from these two, but they're all connected. All of these piles here are connected. And let's say in this subset that I have got A piles, and that I remove them I remove all of the counters in B moves. And the fact that they are connected like this means that B has to be at least as big as A minus 1. Otherwise, we can't connect all of these piles together. Okay, so we've got A piles, and there are m counters in each pile. So am counters in total. And I remove all of those counters in B moves. So each move, I'm taking away m plus d counters. Okay, so those two numbers have to be equal. And I'm going to rearrange this to get m times a minus b is equal to bd. Okay, now b is the number of moves. That's definitely positive. And d, we said, is definitely positive. And so this is a positive non-zero number, which means that this is also. And if this is a positive non-zero number, then a minus b is positive non-zero. So b has to be smaller than a. And that's good news, because now we know what b is. So b is equal to a minus 1. So a minus b is 1, and we have that m is equal to bd. So our pair of numbers that work are bd and bd plus d, which is exactly what we conjectured it might be, because that is d lots of b plus 1, as we wanted. Here's an alternative solution. So we still have m is less than n, and let's let n equal to m plus d again. And we want to show that d is a factor of m. That's the key thing here. So let's assume that d doesn't divide m and see if we can get a contradiction. Well, there are two different types of moves that we can consider. We're going to work modulo d, and we can say that a type A move is when we take a number equivalent to n modulo d from one pile, and we take a number equivalent to 0 modulo d from another pile in that move. And in that situation, we're going to assign a score to each pile. We'll assign a score of 1 to this pile and a score of 0 to this pile. The other situation is where we take a number of counters from one pile that is not equivalent to n mod d. So let's say we have s not equivalent to n mod d. And then from the second pile that we're using, we will have to take a number equivalent to n minus s mod d. And in that situation, we'll assign a score of 1/2 to that pile and a score of 1/2 to that pile. Note now that at the start, the number of counters in each pile is definitely not 0 mod d, because we said that d does not divide m. But at the end, the piles all need to be empty, so they are 0 mod d. And that means that the score for each pile has to be at least 1. We either do this at least once, or if we do this move here, then we're going to have to do it at least twice. So the score for each pile has to be at least 1. And that means the total score when we have finished has to be at least n, because there are n piles. But every time we do an operation, we're adding a score of 1. So that means the number of moves has to be at least n. But the number of moves is m, because we have got n times m counters, and we are removing n each time. So this tells us that m is greater than or equal to n, and there's our contradiction, because we started with m being less than n.